So during Friday's lecture, we derived a mathematical model for the natural response of current and voltage signals in RL and RC circuits. And what we found was that our natural response Yn of time, where this Y sub n could be either a current or a voltage in our system, was given by the mathematical relationship y of 0 minus for t less than 0 minus and y of 0 plus e to the negative t over tau for t greater than or equal to 0 plus, and tau, our time constant, we found to be L over R for RL circuits. I'll make sure to draw that L slightly better. And tau was found to be R times C for RC circuits. So this is just a recap of the natural response. This is all the stuff that we did on last Friday in a nutshell. Okay. So what we're going to be focusing on today is what's called the total response of first order circuits. Our total response, Y of t, is simply going to be the sum of our natural response Yn plus our forced response Yf. So we've already got what looks like half of our situation described. So let's talk briefly about what a forced response means. So we're going to do this for an RC circuit, but it would be a very similar thing for an RL circuit, right? So consider the following circuit where we have a voltage source Vs, make that S look more S-like. Here we have a switch. Here is our resistance R. Here is our capacitance C, like so. And I'm going to call this voltage Vc of t. Unlike what we did last Friday, I'm going to say that the switch closes at t is equal to 0, right? So everything that we did last Friday was disconnecting our excitation source, whether it was a voltage source, current source, or whatever. We were disconnecting our excitation source from our first order network. Now we're taking into account what happens when we connect or leave an excitation source in. So what should our capacitor voltage be at t is equal to 0 minus for this particular circuit? 0, because it's not connected. Perfectly reasonable assessment. what will our capacitor voltage be at t is equal to 0 plus? Still 0, because the voltage drop across a capacitor cannot change abruptly. So whatever value VC had at 0 minus, it must continue to have at 0 plus. What will the voltage drop across the capacitor be a very long time after the switch has closed? Vs. This is our forced response. That's literally it. We have a forcing function, which is the voltage source, that is forcing the capacitor voltage to take some non-zero value at t is equal to infinity, or a long time after the switch has changed state, right? So that's literally all our forced response is. One way to think about what we did on Friday is to say that our forced response was simply 0, because there was no forcing function making it be non-zero, okay? So if we use these results and develop an equation for our total response, and I'm telling you right now that this is going to have an error in it that we're going to fix, so maybe don't write it down just yet. We would see that our total response, y of t, would be y of 0 minus for t less than 0 minus y of 0 plus e to the negative t over tau plus y at infinity. So what I want us to do is just plug in our capacitor values here real quick and see if we can identify what the problem is. Okay. So for the capacitor in the circuit that we have described above, this is going to look like 0 volts for t less than 0, and then 0 e to the minus tau, or excuse me, t over RC plus Vs for t greater than or equal to 0 plus. So what's the problem? It's changing abruptly, right? So 0 times e to the negative t over RC is literally just 0. So we're saying effectively that our value is 0 for t less than 0 minus, and it is Vs for t greater than or equal to 0 minus. So we're going to fix this by modifying how we calculate the coefficient of that exponential. It's going to be y of 0 plus minus y at infinity, which for us would be simply negative Vs. So if we were to plot our capacitor voltage as a function of time for this system, it would look something like this. There's 0, and around here will be infinity. So we have effectively described the charge cycle for a capacitor, right? So that's what it's going to look like if we try to charge a capacitor, and then what we dealt with on Friday was discharging a capacitor. Yes, sir. Which set of brackets? The square brackets. Okay, y at 0 plus minus y at infinity. So we now have a generic equation building off of what we developed last Friday that can be used for any first order circuit, so RL circuit or RC circuit, and technically it can be used whether or not we are interested in only the natural response or we're interested in the total response, with the understanding that for a natural response problem, that y at infinity term is always just going to be 0, right? I'm done. We can work example problems if you want, but that's literally the only change that we're going to see. So when I set up our system of 5 steps, and I included step number 3, analyzing the circuit at t is equal to infinity, this is why. Because in a total response problem, it is no longer 0. And so we're actually going to need to know what value our signal of interest has at that particular time to plug into our generic equation. So we want to work example problems, or you want me to leave you guys to it? Sure, okay. So you have a preference for an capacitor problem or an inductor problem? Start with a capacitor problem. That implies that I might work 2 of them. Why would I need to do that? So let's say that I have the following circuit. Capacitor here. All right, so this is going to be my circuit. I'm interested in the capacitor voltage and the current flowing through the 5 ohm resistor. I'll let you guys pick. Is the switch opening or closing? Closing. All right. Our switch is closing at t is equal to 0. Right. So this is definitely going to be a forced response problem, or total response problem, excuse me, because the 8-volt source is still in some way, shape, or form connected to the capacitor at t is equal to infinity. It would technically be a total response problem either way the switch opens because of the way that I've drawn it, which is why I let you make the choice. So we are going to analyze this using the 5-step process that I developed or that I explained to you guys on Friday. Just as a recap, our first step is to analyze the circuit at t is equal to 0 minus. At t is equal to 0 minus, we are at DC steady state, which means our capacitor looks like an open circuit. So that means we're going to have our 8-volt source here. Here's our 5-ohm resistor. Here's our 10-ohm resistor. This open circuit represents our capacitor. Sorry, this should be 0 minus. Our switch is open. And here is our current IR of 0 minus. So who can tell me what either of these quantities is? Why is it taking so long? I disagree. So Nick Stevens says that VC of 0 minus is 8 volts. How many of you agree with this? Absolutely correct. All right. There can't be a voltage drop over the 5-ohm resistor, nor can there be a voltage drop over the 10-ohm resistor, because they're not part of a closed current carrying path. So the voltage drop over both of those resistors must be 0. So the capacitor sees all 8 volts supplied by the source. Absolutely right. We have accidentally stumbled into the fact that IR at 0 minus is 0 amps by observation. So does anybody have any questions, comments, or concerns regarding the analysis that we've done here at t is equal to 0 minus? All right. Now we will analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is closed. So we're going to have an 8-volt source here. Here is our 5-ohm resistor. With our switch being closed, the 3-ohm resistor is now connected to the remainder of the circuit. Here is our 10-ohm resistor. And much like we did on Friday, we are going to replace our capacitor with a voltage source having the same magnitude and polarity as VC at 0 minus. So this will be an 8-volt source. Here is IR at 0 plus. And because the capacitor voltage at 0 minus has to equal the capacitor voltage at 0 plus, we know this to be 8 volts without doing any analysis whatsoever, because it literally cannot change. Okay. So how are we going to solve for IR at 0 plus? Mesh. Okay. So I'm going to call this I1, this I2. So we would have negative 8 volts plus 5 ohms times I1 plus 3 ohms times I1 minus I2 is equal to 0. And then we would have 3 ohms times I2 minus I1 plus 10 ohms times I2 plus 8 volts is equal to 0. Solving this system for I1 and I2, which is going to take me a moment to do because I made this problem up 3 minutes ago. So our coefficient for I1 is 8. Our coefficient for I2 is -3. Our constant term is -3. Constant term is +8. In our second equation, we have -3 I1. We have 13 I2 and -8. So I got 16/19 of an amp and -8/19 of an amp. From this, IR at 0 plus is the same as I1, 16/19 of an amp. Yes, sir.
Could you have done both divisions?
So you could apply voltage division here if you were willing to do superposition. And figure out the voltage drop over that 5 ohm resistor, the contribution of each individual source to the voltage drop over that 5 ohm resistor, and then use Ohm's law. So you're going to have to wind up solving the problem twice, and I would argue that the amount of work that you were doing is probably a little bit more than doing it, which is why I didn't give Elizabeth too much crap for suggesting it. Seems like a reasonable thing to do here to me. So I personally would have just done probably KCL at this top node. So I would have said the voltage at that node -8/5 plus the voltage at that node over 3 plus the voltage at that node -8/10 is equal to 0. Solve for that voltage, and then 8 minus the voltage that we just found divided by 5 ohms gives it to me. So it's a 1 equation, 1 unknown system, as opposed to a 2 equation, 2 unknown system. But mesh wasn't hard here either, so it seems fair to me. All right, so does anybody have a problem with me saying that IR of 0 plus is the same thing as I1? Seems pretty straightforward there. Anybody have any problems about our circuit analysis that we did here? All right, last check. Did anybody solve this system of equations and get a different number than me? Because it's always possible that I typed it in wrong. All right, so if we all seem okay with what's going on at t is equal to 0 plus, then we'll move along to our analysis at t is equal to infinity. So at t is equal to infinity, our circuit is once again in a DC steady state condition, which means that our capacitor is going to look like an open circuit. Now, it is important here to realize that the switch did not change positions. That's a very common mistake that I see students do, is they effectively revert the switch at t is equal to infinity. They shouldn't. It's still closed. Yes, still closed. So at t is equal to infinity, our circuit is going to look like this. 5 ohm resistor, 3 ohm resistor, 10 ohm resistor, plus VC at infinity, IR at infinity. So who can tell me what's what? I disagree. Not 0. We are analyzing the circuit right now at the specific instant in time, t is equal to infinity. Troy, this is where you would use voltage division. Suggest it. Let's do voltage division. Okay, so the reason why I say that we can do voltage division here is because the 10 ohm resistor obviously isn't carrying any current. So VC is just the voltage drop over the 3 ohm resistor, right? So VC at infinity is going to be 8 volts times 3 ohms over 5 ohms plus 3 ohms is equal to 3 volts. And IR at infinity is just going to be VC at infinity over 3 ohms, which is 1 ohm. Or we could have done it the other way around. We could have figured out that IR is just 8 volts divided by 5 ohms plus 3 ohms, because that's the only path that the current can take. And then from there used Ohm's law to say that VC is I times 3. Either way works. These are the results. Any questions, comments, or concerns regarding the circuit analysis that we've done here at t is equal to infinity? Fairly straightforward. Now we need to determine our time constant. So I very firmly believe that the equivalent capacitance of this circuit is 20 millifarads because it's the only capacitor in the circuit. I need to make sure I'm remembering the number correctly. I am. So that part's pretty straightforward. To determine REQ, we need to look at the dead network during the transient condition. So that's why I'm turning my 8-volt source off by replacing it with a short circuit. Here's my 5 ohm resistor. During the transient condition, my switch is closed, so my 3 ohm resistor is connected. And I look in through the terminals where my capacitor was. So to me, this looks like 10 in series with 5 in parallel with 3. So that's going to be 10 plus 15 over 8. So 95 over 8. If my math is correct. From this, tau is just REQ times CEQ, which I get to be 0.2375 seconds. And the inverse of tau is 80 over 19 per second. Which gets me to my final step. Why is my page being weird? There we go. Plug stuff into our generic equation. To remind you all, our generic equation is y of t is equal to y at 0 minus for t less than 0 minus, and y of 0 plus minus y at infinity, e to the minus t over tau plus y at infinity for t greater than or equal to 0 plus. So for our capacitor voltage, This is gonna look like 8 volts. Sorry, this should be less than 0 minus. And then let's see, 8 minus 3 is 5. E to the negative 80 over 19. Just to be really clear here, this 5 comes from Y at 0 plus minus, or let me write this as VC at 0 plus minus VC at infinity. And our resistor current is going to be 0 amps for T less than 0 minus. And let's see, 16 over 19 maybe? Yeah, 16/19 minus 1 is negative 3 over 19. Any questions? Genuinely asking that. I want you guys to understand that on your next test, which is a week from today, if I'm not mistaken, there's really only 3 pieces of material that are expected to be on there, right? Thevenin and Norton equivalent circuits, inductor and capacitor relationships, and then this transient analysis stuff, right? So this transient analysis stuff is going to be like literally 8 of the 15 analysis type questions, right? On your exam, I break it down into parts. So I'll have you analyze it at 0 minus, 0 plus, infinity, calculate the time constant, and then evaluate the resulting function at some particular point in time. So if this is not making sense to you, it is literally like half your test, at least as far as the calculation bit goes. So if it's not making sense, please, please, please ask, because I would much rather we flesh it out and get you on the same page than you fail your next exam miserably. That's my preference.